And let's try to answer this question in order to understand the quantum numbers and the relationship between different quantum numbers and how they are uh, used to say something about the orbital about the orbitals, and how they are used to next say something about the orbitals. Our orbitals are defined. What are the characteristics? How our orbitals are defined by the quantum numbers. The question is saying what is the total number of orbitals associated with the principal quantum number n is equal to 3. The principal quantum number is n is 3. So what are the orbitals that are associated with this principal quantum number? So the n is equal to 3. The principal quantum number is 3. So what are the possible values of L, the azimuthal quantum number? Right? So according to what we have studied, the value of n, the value of L, azimuthal quantum number, it depends on the value of the principal quantum number 3. What will be its value? It will start from 0 up to n minus 1. N minus 1 is how much? N is 3. 3 minus 1 is 2. So the value of L will be 0, 1, 2. Had it been 4, what will the values of L? It will be 0, 1, 2, 3. Had it been 5, if it is, the principal quantum number is 5, then what will the value, what will be the possible values of L? It will be 0, 1, 2, 3, 4, right? So since this is 3, if the principal quantum number is 3, so there are 3 possible values of L. It will be 0, 1, and 2. The value of n, the principal quantum number, it also signifies how many subshells will be there in the third shell. N means n, the principal quantum number n. N is equal to 3. That means the letter that we use to denote, it also denotes the shell, right? The main shells. So it's first, second, third, K, L, M. So we are talking about the M shell, the third shell. So in third shell, how many subshells will be there? It will be 3. So what I want to say is that the principal quantum number, it not only it signifies which cell it is in the atom around the nucleus, it also means that how many subshells will be there. That means if had it been 1 for first shell, the K shell, there will be 1 subshell. Had it been 2, there will be 2 subcells. Had it been, so it is 3, so there will be 3 subshells. So the value of the L, it tells us how many subshells will be there. And what numbers are used? 0, 1, 2. For 3, the possible values of L are 0, 1, 2. It signifies the number of shells. 0, 1, 2. Now, not only it signifies the number of shells, the value of L also signifies the shape of the orbitals. The shape of the orbitals. What is an orbital? It's a space around the nucleus where there is a very good chance of finding an electron. The possibility of finding an electron is high in orbitals. So when we draw the graph, or when we draw a graph or diagram of where there is a maximum possibility of finding an electron the space, it may be spherical, it may be dumbbell, it may be double dumbbell. So the orbitals may have different shape. So 0 means S. So in order to write the subshell, in order to for our convenience for subshell notation, the values of the numerical values of L, azimuthal quantum number, has been assigned some letters, small letters. 0 means S, 1 means P, small p, and 2 means small d, SPD, right? So now what we have got from the principal quantum number, we have got the possible values of the azimuthal quantum number L, which not only signifies the subshells, but which also signifies, which also tells us about the shape of the orbitals. Yes. So let's move on to third azimuthal number, the third quantum number, the magnetic quantum number ML, whose value depends on the values of L. the value of L depends on the value of principal quantum number, and the value of M, the magnetic quantum number, depend upon the values of L, right? So when L equal to 0, so what are the possible values of M? It will be only 0. How do we do? When the value of L equal to 1, what are the possible values of M? Possible values of M will be -1, 0, 1. Now, how is this written? It's actually we have a formula. The value of M will be, number of values of M will be twice L plus 1. 2 times of L, whatever value is L, plus 1. So when the value of L equal to 1, what are the possible values of M? The magnetic quantum number, it will be -1 to +1 and 0. This -1 and +1, it means this twice L. And the 1, the additional value 1 is that of the 0. So the value of M depends on the negative value of the L to its positive value in the number line. In addition to that, 0 will be there. So that 0 means this number, this value is denoted in the formula by 1. So twice L means whatever the value of L is there, you make it twice. 1 plus 1 is -1 and -1 is 2, right? And then in addition to that, there will be one more additional value, that will be 0. Say like the value of M will depend on the L, and it will go from minus of the value of L to the plus of value of L, including 0. Similarly, if the value of L is 2, what are the values of the magnetic quantum number? There will be how many values will be there? There will be you put the value of L as 2, then 2 times of 2 is 4. 4 plus 1 is 5. There will be 5 values. And what are they? It will go from -1, -L to +L. That means -2 to +2, including 0. So -2, -1, 0, 1, and +2. +1 and +2. So when the value of L is 2, the possible values of M are -1, -2, -1, 0, 1, and 2. So there will be 5 values, and the formula is given by twice L plus 1. So in overall, the question was saying what are the possible number of, or what are the orbitals that are associated when n equal to 3. That means in the third shell, how many orbitals will be there? So this is one orbital. The value of M will decide now the orbital. Second orbital, 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 9 orbitals associated with n equal to 3. That means in the third shells there will be 9 orbitals. The 9 orbitals will have different shape, different size, right? So what are the notations for the subshells? We said that when n equal to 3 there will be 3 subshells, right? And what will be those 3 subshells? It will be 3s for this, for third shell when L equal to 0, 3s. When L equal to 1, 3p, because 0 means S, 1 means P, and 2 means D. So 3s, 3p, 3d. So there are 3 kinds of subshells. In this subshell, since the value of M is 0, so there is only one orbital. So here in this 3s subshell, there will be only one orbital. In 3p subshell, since the value of, and there are 3 possible values of M, -1, 0, and +1. That means there are 3 orbitals possible, right? And it will be, so there will be 3 orbitals in 3p subshell. With the notation 3p is a subshell. There will be 3p is a subshell, and in that 3p there will be 3 kind of p orbitals. So there will be 3 orbitals here. So similarly in this subshell 3d, the possible value of d will be, there will be 5 possible values: -1, -2, -1, 0, +1, and +2. That means there will be 5 possible orbitals in the 3d subshell. Right? So let's count the total number of orbitals that we have when n equal to 3. It will be 1, 2, 3, 4, 5, 6, 7, 8, and 9. So there are 9 possible orbitals with principal quantum number n equal to 3, or in the third shell. in the third shell. So this is how we counted the number of orbitals, but there is a shortcut formula for it. Like when n equal to 3, the n square gives the total number of orbitals possible. So 3 squared is 9. So you can answer this question by simply using this formula n square. So number of orbitals depends on the number of, and the principal quantum number. Had it been 1, the number of orbitals possible will be 1 square is 1. Had it been 2, say 2 square is 4. There are 4 possible orbitals. Had it been, so it is 3, so 3 square is 9, so there are 9 orbitals. Had it been 4 for whole shell, there will be 4 square 16. There are 16 possible orbitals. 16 orbitals associated. Had it been 10th, so it is 10th. If the principal quantum number is 10, the 10 square is 100. So there will be 100 possible orbitals. I hope it makes things clear. These are shapes. S is a spherical shape, p orbitals are dumbbell shape, and d orbitals are double dumbbell shape.